right, we're going to continue on our quadrilateral thing, and we're going to finish these up today. As I said, moving forward through these, we're going to deal with 3 of them today. 2 of them are very familiar. One of them we're going to be less familiar with. First of all, let's start with a rectangle. Rectangle, again, we know most of these things, but here are some things you may not know. All of the qualifications of a parallelogram exist in a rectangle. Both pairs of opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Consecutive angles are supplementary. Now, here's the new thing about a rectangle. A rectangle, there are 4 right angles. So therefore, all 4 angles are also equal to one another because they're all 90 degrees. And the diagonals are congruent and they bisect, which we saw that happening with a parallelogram. But not only are they bisecting like a parallelogram, but they're congruent to start. So when we have that diagonal crossing, we're actually going to have 4 equal segments. So as we look at this one, it tells us it is a rectangle. We would then know all the things about a rectangle. Of course, it's got 4 right angles, but that's not necessary for what we're doing. What they ask us for is the measure of LN, which is this diagonal here, and then also the measure of PQ. Do that one in a different color. All right, so when we learn LN, we're actually going to also know what PQ is, because as we stated at the beginning of this, on a rectangle, each of these segments are bisected and they're congruent to start. So what we're going to do is first learn what LN is. And as you do these things, what you want to think about is, what is LN also a part of? Obviously, it's the diagonal of a rectangle, but as we look at this figure, we can see a side of 6, and then we can see a side of 8. So as we do this, what we've learned is this diagonal is the hypotenuse of a right triangle. And I know it's a right triangle because this is a rectangle, so that's 90 degrees. So a side of 6 and a side of 8. And then we can find our third side. Now this is actually a version of the 3, 4, 5 triangle, but we'll still work this out. Just keep a few things in mind. Remember, this is the hypotenuse, therefore it's got to be the longest side. And 6 and 8 make 14. So we need to have a side that is larger than 8 because it's the hypotenuse, and lower than 14 because the 2 smaller ones have to be larger than the largest one. So we'll just go through Pythagorean's theorem. 6 squared plus 8 squared will give us our hypotenuse squared. So 36 plus 64 is the hypotenuse squared. So 100 is the hypotenuse squared. Therefore, our hypotenuse is a measure of 10. And as I was saying when we first started this thing, that is the 3, 4, 5 triangle, just a multiple of 2. 3, 4, 5. 2 times 3, 4 times, 3 times 2, 4 times 2, 5 times 2. All right, so we've learned that LN, this entire diagonal from here to here, has a measure of 10. And as we stated before, the next thing we're going to look for is PQ, which is this segment here. And on a rectangle, this segment is equal to the segment here. And that segment, of course, is half of the diagonal. So if the diagonal is 10, this one is equal to 5. So now we have a rectangle and we're asked to find the angle measurements of each of these. I'm going to mark a few things that we've already discussed. Remember, these diagonals are congruent to one another. And on a rectangle, this side is equal to this side, and the top is equal to the bottom. So remember this, what we essentially have here is a lot of isosceles triangles. Remember the thing we know about isosceles triangles, if the sides are equal, then their opposite angles are equal. So the measure here of 32 is going to be congruent to the measure over here. This would also be 32. So let's see what angle that is. That would be one of the ones with G in the middle, which is only this one. So J to G to H. So that is the angle that we're talking about there. So this angle measurement would be 32 degrees. So as we think about that, we have the two base angles of our triangle here equal to 32. And then we have a third side, our third angle, excuse me. And remember this, sum of interior angles of a triangle are 180 degrees. So we have 180 degrees inside of this red triangle that I still have marked. And we know a measurement of 32, and then we know a second measurement of 32. So whatever that remains will be this angle that I'm highlighting here, HJG, which is the next one in our list. So we learn that this is 116 degrees. Let's take care of some easy things as well. So we know that if this is 113 degrees, let's just look at the rectangle and just go about what we know. So we know this is 116 degrees. One of the easy things we know about angle measurements is vertical angles. So if this is 116 degrees, the vertical angle is also 116 degrees. I'm going to erase this. Oops, I'll put that back. Erase that for just a second. This one was 32 degrees. Now we also know on a rectangle that the angles down here are 90 degrees because it's a right angle. And the angle 32 is complementary. Remember that word complementary means they add up to 90 degrees. So the complementary angle to 32 degrees would be 58 degrees, which would be this one. And here's the domino effect I was talking about. So if this is 58 degrees, if we look at this other triangle, it is also isosceles. Do it in green here. We have a second isosceles triangle with a base angle of 58, which means the other base angle would be 58 degrees. And then we just recognized over here that 58 is complementary to the angle 32. So if it's complementary to the angle 32, that means that this angle here is 32 degrees. So what we have is two congruent triangles here and here. So if this is 32, this is 32 degrees. And just like down in our corner here, 32 is complementary to 58. So this would be 58. This would be 58. And then on the inside, there's a lot of different ways we can do this. We have a triangle in which we have two of the three angles, 58, 58, and unknown. And we also have what I like to look at is a linear pair. We have a linear pair. This is 116 degrees right here. So the remaining degrees are going to be on the other side. And remember, a linear pair adds up to 180 degrees. So 116 of it is right there. The only thing that's left is 64 degrees. So the vertical angle would be 64 degrees. So we've kind of worked our way through this. And if you wanted to check your answer, what you would be doing was checking to see if the angle measurements of this green triangle that is still highlighted add up to 180. I just put that on my calculator. They do. So that's always a really good sign. All right, now that we've got everything, let's get our answers. So E, angle E to H to J, EHJ. That would be a 58-degree angle. .58-degree angle. Next, we go from angle E to J to H, would be this angle, which we clearly have measured as 64 degrees. Then we are going to look from E to J to F, E to J to F. That's a 116-degree angle. And then lastly, J to E, J to E to F. J to E to F is this angle right here. And we can clearly see we have that angle listed as 32 degrees. So we're going to work a lot quicker through this one. It says find all the missing angles of this rectangle. So we'll take this over to our side here and just take a look. As I said, we're going to work through this quickly. Remember, this side is equal to this side. So if this angle is 41, this angle is 41. We also have congruent triangles on either side. So this angle would be 41 and this angle would be 41. We also know that these two angles are complementary, which means they add up to 90 degrees. So if 41 degrees is there, 49 degrees is right there. And if 49 degrees is here, 49 degrees is there. And the same is also true about the congruent triangle at the top. So we're going 49 degrees, 49 degrees. And then the last thing we need to do is figure out the parts in the middle. These are not perpendicular. The other two that we're going to work with today are perpendicular here in this section, but that is not true about a rectangle. But we do have a couple of 4 triangles, actually. So let's pick this one out. We have 2 of the 3 angles. So remember, the interior angles of a triangle are going to add up to 180 degrees. So we have 41 on each side. So what's left is a measure of 98 degrees, which makes this equal to 98 degrees. And then the last thing we have is a linear pair right here. When you have a straight line, you have 180 degrees. So if 98 degrees is on one side, that means 82 degrees is on the other. And then we have a vertical angle down here, 82 degrees. So we have a bit of a domino effect as we go through these. On this particular one, we're starting in the middle as opposed to the outside. And the easy thing is the vertical angles, of course. So if this angle is 64 degrees, vertical to that is this angle, which is 64 degrees. We also have the linear pair that's formed from the straight line. So linear pairs add up to 180 degrees. So if 64 is on one side, 116 is on the other. Sounds to me like we've already done this one. But that's okay. We can work this one through just the same. So what we have, if we look at it, is an isosceles triangle right there. We know that since those two sides are equal, these two angles are equal. So we're going to take 180 degrees, which is the sum of interior angles of the triangle, and subtract the 64 degrees that we know, which is 116. But those two, that's the remainder of those two, and those are divided evenly amongst each other. So what I'm going to do next is divide by 2. And what I learn is that the other parts of that triangle is 58 degrees, both here and here, which means this is 58 and this is 58. And we also know, since this is a rectangle, that those 4 angles around the outside are all complementary because they're 90 degrees. So if we have a 58 degrees on one side, we have 32 degrees left for this segment. And again, here goes the domino effect. Since it's equal, these are all equal. So moving on to the next thing, we're going to talk about a square. Notice the first things unbolded are just those facts that we learned about a parallelogram. Both pairs of opposite sides are parallel, both sides are congruent, opposite angles are congruent, consecutive interior angles are supplementary. Here's what's different about a square than a parallelogram. Here's one thing it shares with the rectangle. All 4 are right angles. Here's where it's got its own thing. All sides are equal. All sides are congruent. Here's what it once again shares with the rectangle. Diagonals are congruent and they bisect. And then here's where it differs from a rectangle, but it's common to a kite. Diagonals are perpendicular. So it shares everything with a rectangle and then these 2 additional facts. Now the square is usually one of the easiest ones to work because what it essentially does is it constructs, the diagonals construct 4 isosceles right triangles, which we will later know has a name of 45, 45, 90 triangles. All right, so here's where squares are really easy. It says missing sides and missing angles. Well, the missing angles are always this. We're not going to waste a whole lot of time on this. It's 45, 45, 45, 45, 45, 45, 45. You get the idea. 45. And in the middle are perpendicular angles, which means these are all 90 degrees. 90 degrees, 90 degrees, 90 degrees, 90 degrees. All squares will look like this. The only thing we can change is their scale factor. And what I mean by a scale factor is the length of their sides. So on this particular one, we have a side of 4, which means all sides are 4. 4, 4, 4, 4. All right, as I said, this is known as a 45, 45, 90 triangle. If we wanted to find these diagonals, what we will learn later is all we have to do is take the hypotenuse and divide by the square root of 2. We're going to set up Pythagorean's theorem, though, because we do have actually a right triangle right there. And that right triangle can be done Pythagorean's theorem, even though we only have one side, because we know the other 2 sides are equal to one another. We don't know what they are, but we know that they're equal to each other. So it would be leg squared plus leg squared equals the hypotenuse squared. And then we would go from there. These are like terms. So we can do that. We would then divide by 2, x squared would equal 8. And then we take the square root of this number. So these sides are equal to the square root of 8. And this actually simplifies further because 8 can be broken down to 2 times 2. So we have a couple of pairs of 2. So this ends up being 2 square root 2. We kind of jumped ahead of ourselves. We won't do that, and I don't want you to do that on this particular thing because we are going to memorize the 45, 45, 90 triangle stuff. It's worth memorizing. 45, 45, 90, 30, 60, 90 triangle. Not ask you to memorize much this year, but those 2 are worth memorizing, and we will. So one example on a square because they all look the same. We can only change their side length. And then the next thing is the rhombus. This is the one we're a little less familiar with. What it looks like with a parallelogram. Both sides, opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Consecutive interior angles are supplementary. Now let's see what we have. All sides are congruent, like a square. Diagonals bisect one another, like a square, like a rectangle, like a parallelogram. This doesn't give us 4 equal parts. It's actually more like a parallelogram than a square or a rectangle, but they do bisect. Diagonals are perpendicular, like a square, like a kite. And then lastly, diagonals bisect opposite angles, just like a square does. All right? Cutting the angles in half. All right, let's take a look at a few examples of these, and then we'll be done. So let's talk about marking things that we should know about. Here's rules on rhombuses. Okay, this side is equal to this side, is equal to this side, is equal to this side. Essentially, a rhombus is a square that's leaning. The other thing we learned is that the middle is perpendicular. So these are 90-degree angles on the inside here. We also know that this segment will be equal to this segment, and this segment will be equal to this segment. So let's go ahead and just pop down all the stuff that we know without doing any algebra or any math at all. We can leave those there. A little bit of a mess, but we're okay. So if this side is 5, all sides are 5. If this segment is 3, then this segment is 3. So the only segments that we can see that we're missing is VZ, VX, and if they asked us for XZ, which they are, we'll have to know that. So here's what we're going to do. We need to first identify that we have a right triangle that was formed here in the center of this thing. We actually have 4 congruent right triangles. They're just facing different directions. So let's take this triangle, highlight in green here, and lay it on its side. We're a little more familiar seeing what this looks like. So here, here, here. Remember how I told you how popular that 3, 4, 5 triangle is? There it is. This side is 3. This side is 5. That means the other one is 4. But let's just do it. Leg squared plus leg squared, we'll call it x for the moment, equals the hypotenuse squared. 3 squared is 9. 5 squared is 25. When we subtract the 9, we get 16. So x squared equals 16. Therefore, x, square root both sides, x equals 4. 3, 4, 5. Very popular. So this segment here is going to be a measure of 4. All right, so let's plug in our answers here. WX, here to here, is 5. WZ, outside as well, is still 5 as well. We then will look at ZY, also 5. And here we go, working on the inside. W to V, the segment here, that's 3. V to X, it's the one we solved with the Pythagorean theorem. That would be 4. And the outside ZX is a length that consists of 2 segments that are each 4 units. So that makes it 8 units. So this is how a rhombus works. We're going to run to a couple of more of these. And remember, the angles were cut in half. We're jumping to angles next. Just like with a rectangle, these rhombus are going to have a domino effect type thing. So these can go really quickly. Here's what I'm talking about. It said, if you remember in our instructions, that it bisects angles. So if this is 41 degrees, this is 41 degrees. If that's 41 degrees, remember opposite angles are equal. Well, that angle over there is 82. 82. So is this one. But it's 82 divided amongst the 41s. We also know the middle is 90 degrees because all rhombuses are. So the only thing we got left is figuring out what these angles are here. Whatever they all are. All right. So we actually have a large isosceles triangle here to here to here. That's isosceles. So I'm going to take this triangle, I'll keep it green, and put it over here on its side, on the base, where we're a little more familiar with it. So it ends up looking like that. Ugly little triangle, but it is what it is. So this was 41, this is 41. So what I'm going to learn is what that entire obtuse angle is right there. Well, we've got two of the three angles of a rectangle, triangle, excuse me. So we subtract that from 180. 180 minus 41 tells me that the remaining angle is 98 degrees. Well, what's 98? The whole stretch is 98. But remember, on a rhombus, those diagonals are cutting the angles in half. So each angle is going to be 98 degrees divided two ways. So that means this angle would be 49. This would be 49. And then, of course, the opposite side, since they are congruent triangles, will be exactly the same. So now that we have all the information, let's get our answers. This says from Z to V to Y. Okay, well, that's the center angle. So that's one of our right angles, 90 degrees. Next thing, from Z to Y to V. That's the 98-degree angle, but half of it. So that's 49 degrees. And then from W to Z to V, 41 degrees. And then lastly, from Z to W to V, also 49 degrees. All right, thank you for bearing with me so long. Last question. We'll try to go through quickly. Let's zoom in on this rhombus and fill this in where we can see it nice and clear, and then we'll go back and plug in the answers. So again, the diagonals, VY specifically, cuts this angle in half. So if that side's 53, this side is 53. Opposite angles of a rhombus are equal to one another. So if those are both 53, then this side is 53. We also know, regardless of what the other angles are, the middle here is really 4 right angles. Made that kind of ugly there, so let me just put 1. 1 is good enough, actually, because if one of them's a right angle, they all are. All right, so again, we have a triangle. Doesn't matter which one you pick, because they're all 4 the same. We have 4 congruent triangles, so pick the one that you prefer the best. So if I chose this one right here, sum of interior angles is 180. So 90 of it is here. 53 of it is here. So the remainder is going to be 90 minus 53, 37 degrees. 37 degrees. Well, that angle is bisected, so if that's 37, that's 37. Opposite angles are equal, so if that's 37, the other side's 37. So again, just kind of domino effects down as we go. Notice we didn't worry too much about the sides. Outsides are always equal on a rhombus. Diagonals do not have to be. All right, so let's just plug in the answers that we know. So first off, we see from Z to V to Y. Z to V to Y is one of our right angles, so that would measure 90 degrees. From Z to Y to V, that's a 53-degree angle. W to Z to V, that is our 37-degree angle. From Z to W to X, a big angle. It's a combination of two 53s. So 53 times 2 is 106 degrees. And then lastly, we are going from V to X to Y. So that's our outer angle there. 37 twice would be 74 degrees. All right, so the rhombus is new to you. We already talked about the rectangle and square the day before this lesson, so we know what those are. Might have learned a couple of things, but the rhombus is a little unfamiliar, so get yourself familiar with the rhombus. Good luck with your examples.